Okay, so now for some science. Who's ready? So I'm very pleased to begin our session this morning on carbon. Peter, can you just come up here and start loading this up? With a talk from Peter Landschutzer, who came all the way from Max Planck Institute in Hamburg, Germany, to join us this morning and talk to us all about observing variability in ocean carbon dioxide fluxes.
Okay, can you hear me? Great. Well, good morning. Thanks for having me at this really, really wonderful place. And I've been here the last days a lot of times actually next to the sea, watching the sea and being mesmerized by its beauty. And whenever I do that, I get reminded of this plot here. This figure, this image, which I took myself on my first Atlantic crossing, actually. And after 2 days of bad weather and clouds, finally on the third day, everything cleared up, and I got this picture of this very nice sunset. But today I'm not here to talk to you about how mesmerizing the sea is or how beautiful this image is. I'm talking to you about something that is actually very much related to this image. And to help you a bit orientating, so what you see here, this map is like on the top right, Europe, the African continent and the Cape Verde Islands, and then this red dot. So what this image also represents to me is this red dot, and this is the an observational data point that was collected just a few moments before I took this beautiful sunset image. So what I'm talking to you about today is how we can use this point, this red dot, and many others to observe the variability of the global ocean carbon sink. And I put in brackets the bit less sexy part of the title, but a very important part of the title, so based on the surface ocean CO2 observations. And just quickly, I would like to thank Nikki Gruber and Dorothy Bakker, who've actually contributed a lot to what I'll be talking about today. But first, I would like to back up a little bit and talk a bit why it's important to have a new constraint, basically, in the ocean carbon sink based on observations. And I like this illustration a lot. This is from the global carbon budget, but if you go to the latest IPCC report, you'll see a similar one, so there's a few of them out there. And when we talk about the carbon budget for the last decade or the last 2 decades, we actually can break it down to 4 components. And so we've got the emissions from fossil fuels and cement production and land use change. We've got the atmospheric growth rate. And you've got the ocean sink and you've got the land sink. And the question I'm really asking myself today, or in general, is how much varies this land sink? And can we put, with these observations, a new constraint on that sink estimate, on its variability? Because it is important for the budget, and especially also for this term that I'm highlighting now, the land sink, because in budget calculations, as we do them today, or the Global Carbon Project does it, the land sink is actually calculated from the residual of the other terms. So this ocean sink variability might even affect the land sink. So I showed you this red dot in the beginning, and I can tell you there's more than this one red dot. And this is what we have at the moment when I talk about surface ocean CO2 observations, and that's a plot from the Surface Ocean Carbon Atlas database, so the, to date, as far as I know, largest CO2 surface ocean CO2 database, and this is actually the long-term mean I'm showing you from 1982 to 2014. And you see a lot of things just by plainly plotting the data, and what you, for example, see is that you've got still, in the global ocean, a lot of spots where we don't have any data. So, for example, the South Pacific, large parts of the Indian Ocean, and the South Atlantic. But you also see other things. For example, you see that in the Northern Hemisphere, actually, we've got very few places where we don't have observations. And you also see already some typical surface ocean CO2 sort of signatures that we know, for example, the high PCO2 in the equatorial Pacific from the upwelling, and the more in blue, low PCO2 in undersaturated waters of the mid-latitudes, for example. So that all looks good and all looks nice, and we can say like, yeah, okay, we can work with that. We can reconstruct the sea surface PCO2. We can calculate the delta PCO2, the atmosphere, and then calculate the fluxes. But the next plot is intended to show you that it's a bit more tricky than that when I zoom in a bit and show you how many data we have per month. So this is actually, again, the Surface Ocean CO2 database, the SOCAT Atlas database, and this is now January 2010, and actually 2010 is a fairly well observed year. So, so you see where the problem lies, right? So we have to sort of fill these gaps, and we've got actually quite huge gaps. But luckily, we don't start from scratch. Carbon cycle research has been going on for decades, and we have quite a good idea what drives the CO2 in the ocean. So we have got quite some understanding about the physical, the chemical, and the biological proxies of the CO2. But we still have another problem. So let's say we do know all of the sort of the influential factors for CO2, like we have got temperature, we've got the chlorophyll, we've got them even basin-wide. We have another problem. We don't know what's the relationship. So this requires now to go a bit into some mathematical modeling, or to go into some data interpolation methods. And so we've worked quite a lot to reconstruct this relationship by using a two-step neural network approach. So I'll just talk you briefly through this approach. So what we do is we take first a set of input parameters. We use a so-called self-organizing map to divide the ocean into 16 biogeochemical regimes. Now, I mean, I don't want to go too much into detail about what we actually, about the method itself, but I just want to highlight what we want to do with this regions, why we do this regional division. And the reason for that is simple. When you think of CO2 and when you think of CO2 in the ocean, you actually notice that when you look at the time series, for example, there's many signals you can detect. You can detect the seasonal cycle. You can detect the high frequency variability, trends, and internal variability. And the way we designed these regimes is that they actually move with the seasonal cycle of PCO2. So that's why we have, for example, PCO2 climatology of Taro Takahashi as an input here in this first step. So basically, the seasonal cycle is in many parts of the ocean actually the strongest signal. So by designing these regimes to move with the seasonal cycle, we actually eliminate one of the strongest and most intense signals, and with the idea that with the rest of the signals that remain in these regimes are internal and decadal signals. So then for each of these regions, once we've divided them, we go to the second step. And this is a so-called feed-forward network. Well, for those, to make it simple, for those who are familiar with regression models, the principal idea is the same. So what we do is we have a set of inputs, and we try to establish a function to link them to the output, which is, again, our observations from the database. And but instead of a general linear regression model, we do use a non-linear regression method. Since I told you we don't know what the exact relationship is between our inputs and our outputs, we don't want to make any assumptions, so we don't want to assume that they're linear. So once we do that, and once our smart method has established the relationship between our inputs and our outputs, where we have data, we can use this relationship and then fill the gaps where we don't have data. And once we've done that, we end up with that. So this is the interpolated sea surface partial pressure CO2 from 1982 to 2014. So exactly the same time period I showed you earlier where we had observations. And what's actually new for those who are a bit familiar with my previous work, what we're working on at the moment is also to include coast and marginal seas, but this is very much ongoing work, but I still wanted to show you sort of a bit of a teaser that we are going in that direction as well. Well, now this is a map, right? This doesn't tell you much, so you obviously want to know how good is it, how well is it reproduced, how well is it how well do we represent data, and so we do a big deal in trying to evaluate our method. So, I mean, the good thing to have at the moment two databases, so the SOCAT database and the LDO database, is that, well, you've got data in one database that are not in the other. So we're trying to use as many independent observations to evaluate our model, which is just outlined here on the left-hand side. But we also try to make use of time series stations. For example, here on the right-hand side, you see the combined record of Bermuda and the hydro station S, so that's the hydro station S, and really try to understand if our method is actually capable of reproducing all these signals, like the seasonal cycle, can reproduce trends, or internal variability. So once we've done that, and once we are reasonably happy with what we get, we can calculate the fluxes. And this is now the air sea flux density of CO2 between the atmosphere and the ocean in moles per square meter per year. And just to let you know, red means the ocean is gassing CO2 into the atmosphere, and blue means the ocean is taking up CO2 from the atmosphere. So on top you see that the year of the reconstruction, and then the quite fast running number is the month of the year, and you see quite some seasonal variability. You see, well, not so well the internal variability yet, but I'll come to that in a minute. But yeah, you see quite some shift between in and outgassing. So what you didn't see very well from this animation is actually what the variability is. And let me show you in the next plot. When we integrate this air sea flux density globally, then we find this. And what we see here, I'll talk you briefly through this plot. So you see in the colors in the background, the shading, the contribution of each basin. Now they are now separated at 44 south, so it's a clean cut. So you have in dark blue the Pacific Ocean, light blue the Atlantic Ocean, light red the Indian Ocean, and in dark red the Southern Ocean south of 44 degrees south now. The solid black line is the global integrated uptake, and then you see in the dotted hatched area the uncertainty of the method. And what's very interesting is when you compare this line, this solid black line, to this dashed line. And this dashed line is actually derived from an ocean model where we actually turn off climate. So basically what's left then is the uptake we would expect from the ocean just based on the increase of atmospheric CO2. And you see actually quite some departure of the solid line from this dashed line. So, which very much points in the direction that there's actually quite a substantial amount of natural variability in the ocean. So, you might now say, like, okay, this is the method. The method is not able to get the internal variability right. So, when I show you this plot, that is actually not dependent on the method. That's what we just see. So what you see here is a plot from a project, the Surface Ocean CO2 Mapping and Comparison Project. This is led by Christian Rödenbeck. And it actually combines, at the moment, the 14 mapping methods, which use, well, partly the same data, partly other versions of the database. And you see it's a bit all over the place, so there's quite a lot of disagreement. But again, I want to talk today about the variability, and so I've highlighted it in the two shadings, the gray shading and the red shading, two periods, the 1990s and the 2000s. And despite them being quite all over the place, and the methods being like very different, ones are regression models, the others are more process-based models, you actually see that all of them agree that in the 1990s we actually had quite a stalling in carbon sink, if not even a reduction. Whereas in the 2000s, all but one actually agreed that there was actually a strong sink increase. So again, a sign of the natural variability. And now I want to go a bit into detail where this variability comes from, and I dive into two basins out of time reasons. And you see on the top is the Pacific Ocean, and on the bottom the Southern Ocean. And you see two Hofmüller diagrams of the air sea flux anomaly, of the zonally integrated anomaly of these two basins. Now I have to caution you, the Southern Ocean now extends a bit further north, so it's extending to 35 degrees north. And what you see here is actually very clear that a lot of the interannual variability, as we would expect, comes from the equatorial Pacific. And it might not be too obvious here from this blue square, but it actually very nicely matches the ENSO variability that we see in the equatorial Pacific. But what is a bit more puzzling, or what was more surprising, not so much puzzling, but more surprising, is that actually the decadal variability stems more from the high latitudes. So for example here, the high latitude North Pacific and the Southern Ocean, to quite some substantial decadal variability. And what you also see within this space is that actually in the late 2000s you see quite a substantial negative anomaly, so strong uptake by the ocean. And I'm not showing you the Indian Ocean and the Atlantic Ocean, so I hope you believe me that you'll see actually the same thing there. So you see this increase in all basins. And now I would like to talk a bit more about the Southern Ocean, again out of time reasons. And the reason for that is because in the late 2000s there were quite a large amount of papers that actually suggested that the Southern Ocean carbon sink has at least not continued to have its full potential. So there was actually a saturation of the Southern Ocean carbon sink. So when we go and have a look at the Southern Ocean, we find this. So again, what you see in blue is the method I was presenting you today. In orange, you see one of these methods that are within this surface ocean mapping comparison project. And then in black, you see an atmospheric inversion based estimate. And again, this time in black solid, this expected uptake if you would run this model without climate variability. And you see in the Southern Ocean very much what you saw globally. You see first the departure of this expected uptake, like very much in agreement with all these studies that we had in the late 2000s. But then after 2002, we actually see this very substantial increase. And actually all methods, all three independent methods, do show that the Southern Ocean carbon sink actually gets back to expected values. And it was, now this particular plot shows two methods based on surface ocean PCO2 observations. But as I showed you earlier, we've got more available from the surface ocean CO2 mapping with the comparison project. And so I was very interested to see if really all of these methods show that. And this is now delta PCO2. I'm sorry, before that I was showing you the flux. But what you see is like in black the individual lines of these methods, in red the mean, and in the red shading the standard deviation. And despite them having quite a difference in the absolute, so they don't always agree on the absolute delta PCO2, all of them actually show this increase in delta PCO2. So all of them actually confirm basically this Southern Ocean uptake increase. Now, obviously, what drives this uptake is the next important question that we're very interested in. Why is it happening? And the first thought we had was, okay, the suggestion in the late 2000s was that the saturation was due to the increase in the westerly winds and the poleward shift of the westerly winds. So, well, it is very sort of good first-order assumption to think that this has changed over the last decade. But it was actually not the case, and we found that actually the winds haven't really weakened, or they haven't the poleward shift hasn't stopped. But what we found actually is that when we look at the basin at the Trenton, this is now for the last decade, again from the method I was presenting you today, divided into thermal components, so basically the temperature-driven trend and the non-thermal components, so everything that is not temperature-driven. So there might be biology, there might be DSC, there might be upwelling. We actually see substantial differences between the individual basins. So we see actually in the Pacific still quite a strong increase in the non-thermal PCO2, so actually suggesting that the upwelling hasn't stopped. So there's still quite a lot of DSC being upwelled, leading to an outgassing of this non-thermal component. But on the other hand, we also see that we have a cooling, and that would actually suggest more uptake. So what we then looked at is a bit more into detail about the weather that was going on there in the Southern Ocean over the last decade. And what we found was actually very surprising. We saw that we saw quite a pressure asymmetry. So what happened is not that the winds have weakened at all, which they have not. But what we found is that we had an intensification of the Amundsen low in the Pacific sector and high pressure area in the South Atlantic. And what happened is, and the winds have not weakened, but the wind belt has sort of slightly shifted, if you want, following this pressure area. So what you have in the Pacific sector is more colder water coming from the Antarctic continent, which is actually dominating this DRC and alkalinity-driven upwelling trend that we saw. Whereas in the Atlantic sector, we see the other way around. Even though we've got a warming, which would actually suggest increased outgassing of CO2, we actually see that we actually have much more dominating DRC and alkalinity-driven trend, which overall for both sectors mean that we have an increase in the air-sea gas flux and an increasing uptake in the Southern Ocean. So to just quickly summarize this up, so the three main points I tried to get across here today are that the surface ocean PC2 observations suggest actually strong decadal variability. The next point is that the decadal variability stems from high latitudes and the internal variability more from the low latitudes. And that the global ocean, in particular the Southern Ocean CO2 sink, has strengthened in the most recent decade. Thank you very much.
Hi, so can you go a little bit on your previous slide? I guess I was,
This one?
can you say 2 words, about how come if you're warming, your DIC is going to go the opposite way? Is that your red blob is going to be a region that's biology dominated? What do you mean by DIC alkalinity driven trend?
So basically what you, the biology question is a good one, but what I mean with that is, so sort of what we show here is when it's, okay, I'll start all over again, sorry. When we do the division into the components of what can drive our PCT, we can only divide between temperature and non-temperature. So basically what that means is thermal means it's temperature dominated, fluid it is the rest. Now biology is a good question. We have tried to look at that. We were looking at the ocean color data, but we couldn't really detect the trends. So the issue we had there is because of the missing seasons in the Southern Ocean, that we could not pin down biology as a driver. But that doesn't mean that it doesn't play an important role there. It's just that we couldn't show it from the data we had. If that makes sense.
Hi, thanks. That was a great talk. I had a question about when you were predicting PCO2 using satellite observations, you can essentially hindcast as well. And if you can do that, then you can completely take out the assumptions of disequilibrium that people have to make between the atmosphere and ocean. And I was wondering if you'd looked at the variability in the disequilibrium over that time period.
You mean that the delta PCO2
Yeah.
between the atmosphere and the ocean? Yes, I mean, what we've done, I've sort of switched a lot between fluxes and delta PCO2, but what I have not shown you is that where we found that the delta PCO2 is actually driving the flux. So if you think of disequilibrium variability, it is more or less the same as the flux variability. So it's also very strong disequilibrium variability in the same direction as you see the flux variability, because we found that the changes in wind and solubility are actually very small compared to the delta PCO2.
Okay, two-part question. One is here the pattern that we see in this slide is actually decadal variability. Is it imprinted though warming trend on the on the southern annular mode, or is it, for example, the natural variability of the system and how that changes?
Yeah.
And then the second question I have, you do mention the dependence of the wind, and we all know how sensitive the flux is on the wind speed, but in your neural network method, you didn't include surface wind forcing.
Okay, first to the southern annular mode. I mean, yeah, you're right in that these studies that suggest that the weakening of the sink linked it to the southern annular mode. But what we found is that it's not as simple to link the last decade to the southern annular mode, because if you actually look at the data of the southern annular mode, you see that it's peak in 98, and then you see more or less a leveling of the southern annular mode. So no concrete trend, or at least this trend would not necessarily match this. So I think, and we've actually pointed it out on this slide, so if you look at the top right, we actually believe that it's got something to do with teleconnection patterns. So it's not solely the southern annular mode, but maybe the teleconnections with other oscillations. Then to your second question about the wind speed, yes, it's not included in the neural network method itself. It would be worthwhile testing it, yes, if that would make a big change. No, exactly. This is what I was pointing out earlier when I show you the delta piece. So just this equilibrium, actually that is the main driver of the Southern Ocean internal variability. It's not the wind variability. Excuse me? In the Southern Ocean, yes. So it's not the change in wind strength. I mean, what we argue here is that the wind patterns change. So the sort of the place where the upper is placed. So not the strength of the wind, but sort of where the upper is placed.
So let's thank Peter one more time.
Thanks, I got it.